Okay, so now we're going to be looking at how do we construct those those motion schemes for the follower on our displacement diagram. Okay, so we already looked at the displacement diagram in that previous example, and as we said, a displacement diagram is going to represent that motion. It's a graphical representation of the motion that that follower is going to take. That y-axis or that vertical axis is going to be the distances that that follower needs to move. And then the horizontal or the x-axis is going to be that angular displacement. So that's going to be our one revolution, 360 degrees. Okay. Now, displacement diagrams give that graphical representation. They must be drawn to scale. And that's the part that we're going to, and you're going to draw in AutoCAD. In this lecture, I'm not going to demonstrate AutoCAD. I think you guys know how to do that. I don't want to waste time, if you would, kind of showing you that stuff because you know it, all right? And you've gotten some good practice in the things that we've been looking at in previous modules. But I'm going to be kind of, talking about the diagrams, and what I want you to make sure that you're doing is thinking about how you're going to create it in AutoCAD, which I have no doubt that you have the skills to do. So I'll kind of give you hints and some not tricks, but hints along the way. Now, there is a wide variety of different motions that our follower can take, but we're gonna look specifically at four main kinds. Okay, four main kinds. And as we look here, the objective of these schemes is to produce a movement that is going to have smooth accelerations. Okay, smooth accelerations. So if we have a slow moving cam, it can take higher accelerations because there's not going to be that opportunity for that follower to become disengaged from the cam profile. Also, there's going to be less chance for jams or things going awry. Okay, so if it's slow moving, pretty much any one of these motions can be used on the cam. Okay, now you might ask, well, what is slow moving? When we're talking less than 100 RPMs, that's a pretty slow moving cam. We mean one revolution in a minute. Okay. But once we get above 100, then we're moving fast enough that we want to take that into consideration and want to avoid some of the motions that, could have higher accelerations that could create either jumping off of the profile of the cam or jams. Okay. And they also could cause some vibration as well. So, couple different vocabulary words that we haven't come across yet so far. So the first one is going to be total follower displacement. The variable h is going to be used for that. And h is really just considered like a height, if you would. Okay, so that's going to be the total follower displacement for whatever the rise or fall is in the segment of motion that we're looking at. Okay, T we already looked at. Capital T is the total amount of time in a period. And then the small letter t here is going to be the time of a rise or a fall interval. Okay. B or beta is going to be that rotation angle. We saw that. Theta is going to be the angle of the rise or fall interval. So we're going to kind of see it's going to be the angle of the line or the slope of the line. And then our W is going to be our angular speed of that cam, which we're used to. R is going to be follower displacement, and then V and A are going to be our traditional velocity and accelerations. Okay. As we look at motion schemes, the motion schemes are going to set for us those radiuses in and out of that sequence of motion that we're looking at. So, for instance, if we look back at figure 9.6 on page 227. Okay. When we looked at our displacement diagram here at the end of example 9.1, I told you that these radiuses going in and out of the motion. So this first motion is a rise of 2 inches in 1.2 seconds, if I remember right. Yes. This radius going in and out is going to be constructed based on the type of motion scheme that would be specified. So not only do we know that this is going to rise 2 inches in 1.2 seconds, but we also have to get the information of what is the motion scheme. And they didn't do that in this first example. They were just kind of introducing some of the concepts. So that additional bit of information is going to help us to construct that curve going in and out of the motion. Okay. You'll notice we also have curves here going in and out of the motion. And then lastly, falling as well. The dotted lines in the background are just kind of the start to the finish. Okay. So knowing what the motion scheme is going to help us to finish the construction of that displacement diagram. Now there are 4 kinds of motion that we're going to be looking at in this particular section. So the first one is called constant velocity. Okay, constant velocity. We're going to see the curve, the displacement curve for constant velocity on page 229. Okay, and you're going to notice that in this figure 9-7, there are 2 columns. There's 3 illustrations in the left-hand column and 3 in the right. So constant velocity are the 3 on the left-hand side here. So the top illustration is looking at follower displacement. So this is how we would see it, if you would, on the displacement diagram. And it literally starts from 0 and is a straight line all the way up to the top of the motion. So in that first sequence, it would be, if you would, starting at 0 and going straight up to 2 inches in 1.2 seconds. Okay. Now, you'll notice, first of all, we don't have any curves in and out. All right. Because on our illustration, in our example, there were these curves here and there aren't any here. Exactly. So constant velocity is, we're going to start going at that speed right away. Now, as we see here, that means that at the start, we're going to go immediately to the angular velocity that we need to achieve that. Okay. And we're going to stay at that for the entire time, and then it's going to drop off. In practicality, or in practice, that's really not possible. We have to have some sort of a ramp up or a speed up or an acceleration, right? To actually do that. Because otherwise our accelerations, they actually go to infinity on either end, and they're not accelerating in the middle, because then you have that constant velocity in the middle. Okay. So even though this looks very simplistic, in actuality, it's not practical or really possible to do it in its purest sense. There's going to be some sort of a speed up and a slowdown, or an acceleration or a deceleration. Okay. So even though this is considered one, you would have to use it for very, very low speeds and high forces so that you continue to get constant contact between that cam profile and the roller or the follower. Okay. So this is the first one, constant velocity. Okay. Again, low speed applications or not at all. All right. The second one that we have in here is going to be a constant velocity fall. So this was a rise, and then this one is a fall. So you'll just notice that it goes in the opposite direction. And then we have the decelerations and the velocities falling in the opposite direction. So it's just that. We are going to focus only on the displacements of any one of the motions that we're looking at. We won't be calculating the velocities and the accelerations. Okay. As we turn the page, the next kind that we have. Oh, and I should say, as we look at constant velocity, it's literally connecting where you start to where you finish with a straight line. That's the construction, and that's it. When we start looking at the other 3, now we're going to have a little bit more construction, because we're going to notice that as we look at constant acceleration motion scheme, we now have a little bit of radiuses going in and out of our motion. So if we would start from beginning to end and just draw, and I'm just going to kind of draw it here as an illustration. If this was constant velocity, that would just be a straight line. But notice now we have the curves going in and out. As you can imagine, this is going to create for us a smoother transition as we rise and fall, or go from one motion to the next. So what we end up getting then is a velocity curve that speeds up to its highest velocity and slows back down when it gets to the top of its motion. Okay, so we're accelerating and decelerating in and out of that motion. And then you're going to notice here that we do have an abrupt start and finish to our acceleration, but at least it's not like to infinity in two different directions and then constant, or zero acceleration in between. Then you'll notice that we have the constant acceleration fall on the opposite side. Now, to construct this, all right, it's not just random curves in and out. We would construct it doing the construction that we see down here. All right. Now, the examples that you're going to be doing for our module 7 practice problems don't involve the constant acceleration, and the problems that I have assigned do not involve constant acceleration, mostly because they're not used as much, okay, for the reasons that we see here with the acceleration, and it'll make more sense when we look at the last two. But to construct it, you're going to notice that you have this illustration down here. And basically what you do is you find what your total time is. You're going to divide it in half, okay? And divide it in half over the height or the rise that you have. So the rise is here, whatever the total rise would be. And then this is the time that it takes to do that. So you're going to create, if you would, 4 quadrants, in half this way and half this way. Then you're going to start at the bottom here, and you're going to find 1, 2, 3, 4 even divisions along that vertical line to the middle here. And then you're going to simply construct the lines to connect those from 0. Where the first one at the bottom here crosses the 4 divisions here is going to be the first point, second point, third, and then fourth. And then you're going to create a spline, a best fit spline to go through. You can recreate that construction on the top here, but you can simply, as you can imagine, mirror twice to get it to be, the curve on top, and then you're going to do a spline through those points as well. Okay, that's how you create the curves going in and out. You construct them, and you would do it again with a CAD system, a 2D CAD system, to get it nice and accurate. Okay, so that's constant acceleration. And again, I'm kind of breezing over it to kind of show you the progression here, but you won't be constructing this for examples or problems. But the last two that we have are harmonic motion, and then we'll have one more cycloidal, we're going to call it. But looking at harmonic motion, you're going to notice we have 3 curves here. This is the displacement on the top, this is the rise, and then this is the fall. Here again, you're going to notice that we have those radiuses coming in and out. But now we have a curve for the velocity that is more curved and more gentle, which will then allow us at higher speeds to ensure that we don't have jerkiness. So if we compare back to constant acceleration, if we look at the velocity curve, see how there's a curve on the top? Over here, there was a point on the top. And then as we looked at the acceleration, this is constant acceleration. We've got 2 boxes. Now look at the acceleration. Now we've got curves in our acceleration, okay? So again, it's going to be a lot smoother operation, especially at higher speeds. Again, greater than 100 RPMs is when we start looking at making sure that we have things that are going to remain in contact and not have jamming or non-contact as it moves, okay? Now, to construct the harmonic motion, and you will have one of your assignments is going to do this. So harmonic motion construction is at the top of page 232. And what we're going to do is we're going to look at the total rise vertically. And then the horizontal is going to be the amount of time or the period that we're going to be using. Now, for harmonic motion, we are going to be dividing in 6 sections. So along the horizontal axis, however long this is, you're simply going to divide that number by 6 and have 6 even increments along that length, okay? In AutoCAD, there is a function called divide. You can divide a line into however many equal sections that you want, and it's going to put a point or a note at each one of those. If you want to use that command, you can in AutoCAD, all right? Or you can simply divide that by however long that is, and then, increment off that way. So you're going to divide this into 6 even sections, okay? And then you're going to notice that here, whatever that height is, you're going to divide by 2 to find the center. And you're going to create an arc that is going to have a diameter equal to the total height. So in that first example, our total height on the rise was 2 inches, okay, that would mean that you would have a circle with a radius of 1 inch here, okay? Then what you're going to do is you'll notice that we have 6 equal divisions here. Since this is 180 degrees, every 30 degrees, you're going to mark off a division, okay? And then what you're going to simply do is where it crosses that arc, you're going to go horizontal across to where it's going to cross with the first division here, and that's going to be your first point. 2, 3, 4, 5, and then 6 at the top. Those points then are going to be the points that you're going to create a spline, a best fit spline going through those points. Okay, and that's going to be how you construct in AutoCAD. The harmonic, in this case, it's a rise. If it would be a fall, it would be on the other side, and it would just start with 0 here and then go down to 6 down here in the opposite direction. Okay, so that's harmonic motion. Again, you will have one of your assignment problems is going to deal with harmonic motion. So you'll be going back to this illustration to just kind of reference the construction. Okay. Then as we look at the last type, this is cycloidal motion. Cycloidal motion, the displacement diagram, you can see we have curves going in and out. And then here again, we have a curve going into the velocity with a curve at the top, and it has the best acceleration profile as well. So here again, when you have very high speeds, chances for jams that you don't want to deal with, cycloidal is the way to go. And you might say, well, why don't we use cycloidal all the time? You could, but it just gives you another option. Okay. So as we construct cycloidal, this is down here, little bit different. You're again going to work with 6 divisions. Okay. So 6 divisions along the horizontal axis for the time frame that you're dealing with. Okay. And then you're going to notice that we have a full circle this time. As we look at the top, the middle, and the bottom, so this would be a continuous line. This is going to be the axis that the center of our circle for the cycloidal motion is going to be on. Zoom out here a little bit. Okay, so this goes through points 0, 3, and the end, which would be 6. Okay, they all meet at the center here. Then our diameter, okay, our diameter is going to be 2 times the radius. And this is the equation. The radius is going to be the height divided by 2 divided by pi. Okay, that's going to be the radius. So if we multiply that by 2, that's going to be the diameter. We are going to then divide that circle into 6 equal segments. So these are 60-degree angles. Do you see that? Okay. And now where they meet in the middle. So you're going to notice that 0, 1, 2, 3, 4, 5, and 6. 0, 6, and 3 all meet in the middle at the center. So that's why we have 0, 3, and 6. Correspond to 0, 3, and 6. Then if we look at 1 and 2, we're going to meet those 2 in the middle. And where they meet in the middle on that horizontal line, again, this is going to be your construction. You're going to go up parallel to this line. And where it crosses with 2, doesn't cross 1, it crosses 2. I'm sorry, 1 and 2, 1 and 2, sorry, 1 and 2. That's where that one's going to go. Then for 4 and 5, horizontal line across at that intersection, parallel, 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 4 and 5. Once you have those points, best fit spline through those points for the in and the out. Okay. Again, not going to demonstrate the AutoCAD, but just kind of giving you spline. You cannot straight line connect the dots. All right. That's not acceptable. You have to use the spline function. The spline function is going to be under the draw menu. There's going to be a little line down, and then there's going to be extra boxes underneath. Okay. If you need to find it, just ask me and I can give you that insight when we get there or when you get there. Okay.
Can I ask you a question?
Of course.
Yeah, sorry. That circle kind of down to the left, is there a certain angle the center of it's supposed to be from the bottom horizontal line, or how do we know?
Nope. It's going to be constructed from the last division point, number 6,
Mhm.
and then it's going to connect all the way through to 0. You
Okay,
see that? And then that's going to be the line that's created. So that's going to be determined by, if you would, how long or the slope of that would be.
got it. Okay, thank
Yeah,
you.
and then this would be your total height, your rise, if you would.
Hmm.
Hmm.
Yeah.
Yeah. Yeah, good question. Thank you. Any others? And again, this will be one of the profiles that you're going to be using. Actually, the example that we do here for our last module practice problem will utilize cycloidal. So we'll look at that more closely. Okay. And then you have an assignment problem that'll do that as well. Okay. So let's take a peek at our example. Let me catch up our PowerPoints. So we did our follower schemes. And we already did 9-2. So 9-3, oh no, I guess it is 9-2. 9-2 and 3 are going to be our last problems. They go together. Okay, they go together. So let's take a peek starting on page 234. Okay. What we're going to do is a cam is to be designed for an automated part loader as shown down here. Okay. And basically what we have going on is that this is going to push in and out, in and out, in and out. Okay. And here's the rotation, here's the cam, and then here's our follower. Okay. Now it says using the motion equations, construct the chart that tabulates follower displacement versus time and cam rotation. You are not doing that. I crossed that out. Okay. And it would be creating a chart every, quarter of a degree, if you would, or time every, I don't know, however many degrees here, what the follower displacement would be. We're not doing that. Okay. That's an Excel spreadsheet. I'm not doing that application. We are going to draw the displacement diagram. It would be creating the displacement diagram, but you would be drawing it in AutoCAD. All right, we'll talk through it, not draw it or demonstrate it here, but we will talk through it. It says plot the data of the motion, which would be in a displacement diagram. Okay, so now we are given at the top here the motion sequence. So it says we're going to rise 50 millimeters in 1.5 seconds using constant velocity motion. Then we're going to return in 2 seconds using cycloidal motion. And then we're going to dwell for 0.75 and then we're going to start over. So essentially it's really 3 steps and then it's just telling us to repeat. Okay. So 3 steps here. So what we're going to do is we are going to first go through that same process where we're going to calculate, as the problem states here, what is the total time for a full cycle? Okay. So underneath here, go zoom out just a little bit. This is example 9.2. And again, this starts on page 234. Okay. Now the given information is the sequence. I'm not going to rewrite the sequence. So we're going to jump right in. And step number 1 is the total time is going to be T1 plus T2 plus T3. There's just 3 steps here. There's a rise, a dwell, and a fall. No, a rise, a fall, and a dwell. Sorry. Okay. So the times for this from the problem, T1 is 1.5 seconds. That's when we rise 50 millimeters. T2 is we're going to go back down 50 millimeters, but we're going to take 2 seconds to do that. And then T3 is a dwell of 0.75 seconds before it starts over again. Okay. So our total time should be about 4.25 seconds. You guys get that same number? Okay, good. All right. Now what we're going to do is we're going to use that information to calculate the rotational speed of the cam. Okay, the rotational speed of the cam. So number 2 is going to be W. Angular velocity of that cam is going to be equal to how much time it takes to go around 1 revolution. And time above here is that. So this is going to be summation TI, right? So we know that 1 revolution is going to be in 4.25 seconds. So if we divide that, we're going to get 0.235 revolutions per second, right? It's going to be equal to our W. All right, I'm going to put my little circle around that one. But if we wanted to let somebody know how fast we're going in RPMs. And this also helps us to qualify the speed of our motion. Like I said, slow moving is about 100 RPMs. Okay, anything above that starts to be moderate or fast speed. So let's just see where we are in our RPMs. So if we take this 0.235 revolutions per second, just want to convert that to revolutions per minute. So we're going to keep the revolutions up here. We have seconds on the bottom. We know that there's 60 seconds in 1 minute, right? Seconds cancel. So this is now going to be in revolutions per minute. So 0.235 times 60 looks like that's 14.1 RPMs is equal to RW. And it's just another way to express it. It's not really part of the problem, and we're not going to end up using it, but we can see that we're down at 14.1 revolutions per minute, which again would be considered a slow moving operation. Okay. So questions on that so far. We always have to calculate what is the total time, and then using that time for one revolution, how fast are we going? Okay. What is the angular velocity of that cam? Now, step number 3, we want to know how many degrees are taken up of the revolution, the one revolution, for each one of these sequences along the way. So this is going to be our betas, right? So our beta 1, for instance, is going to be the angular velocity of the cam times its time for that particular motion, okay? Now, our times are in seconds, just like they were in the previous example. So we want to multiply the revolutions per second, the 0.235 revolutions per second, not the RPMs, okay? So we're going to say, all right, our W is 0.235 revolutions per second. Make sure you put your units in. And our time is 1.5 seconds. So seconds cancel top to bottom. And our beta 1 is going to be 0.3525 revolutions, right? Now, we want this in degrees, don't we? Not in revolutions. So we do a quick conversion, right? We're not afraid of that. One revolution on the bottom, 360 degrees on top. Cancel out revolutions. And we'll multiply that number by 360 is going to be 126.9 degrees is equal to my beta 1. So I'm going to put a little cloud around that. They rounded up to 127. So our numbers are going to be slightly off, but that's okay. I think it's good to hold at least one decimal place on our degrees. So now we want to do that same thing for beta 2 and beta 3, or time 2 and time 3. So I'll do it on the side here. Go ahead and do that as well, and make sure that we get the same numbers. So once I get done, these are the numbers I come up with, and they're slightly off from the book, just a little bit, but I did them a couple times and I'm very confident in my numbers. Did you guys get the same thing? Okay. And then when we add up the betas, I get 359.6. Make sure that you do that step. Again, it's just a confirmation that you have one revolution for each one of your times added up. Okay. All right. Everybody ready to move for our next step? Okay. So now, as we look at the problem in the book, I'm going to go back over here. They wanted us to, using the motion equations, create a table. That would be programming with Excel. That is step number 4, and then creating an Excel. We're not going to do that, okay? What we're going to do is, this is where we're going to stop for example 9.2. So you want to have your total time, your rotational speed, and all of your betas, okay? And that's where we're going to stop with 9.2, and then we're going to continue to 9.3 for finishing up. So if we look at problem 9.3, which is on page 236, okay? It says here, the application presented in example 9.2 graphically construct the follower displacement diagram. So we're going to talk this through, okay? So again, I'm not going to demonstrate in AutoCAD how to do this. What I'm going to do is I'm going to kind of talk it through and relate the numbers that we had gotten and what we see here in the construction. Okay. All right. So first of all, the motion that we were given, okay, is going to be back to the first 3 steps, if you would, or the 3 steps in the motion of 1 revolution. We have a rise of 55 millimeters in 1.5 seconds. We have a return, meaning it's going to go straight back down in 2 seconds. So it's going to go 50 up and 50 down. Even though it's not saying I'm going to fall 50, it says return. That means you're going right back to 0 in 2 seconds this time. And in each one of these, for the rise, we're going at a constant velocity, and in the fall, we're using cycloidal motion. So this is how we're going to construct the curves going in and out, okay? And then lastly, we're going to do a dwell of 0.75 seconds, okay? So let's look at our diagram, okay? So in the diagram, just kind of reviewing, our diagram gives us a graphical representation of follower displacement versus degrees along cam rotation. Okay, so as we look here, follower displacement, the highest number is going to be the highest value that we need to go to. In this case, this is in millimeters, so it's 50 millimeters is the top number, and it also is the highest point on our curve. Okay, now for this one, for the first sequence, okay, the beta 1, that was 127 degrees, okay? When we calculated our beta 1, I got 126.9, okay? They rounded to 127, which is fine. So when you construct the length here, okay, remember, we want the length of our x-axis to be 3 times the height. So if this is 50 millimeters, do you see how this overall height is 150 millimeters, right? 3 times. So you would make that proportionally, the length is 3 times the height. Okay, that way, again, you don't get too long or too short, right? So that's going to be 150 millimeters. Now, we have 3 time frames. We have beta 1, beta 2, and beta 3, which we calculated. 126.9 or 127, 169.2, and the 63.45. Again, adding those up, we get 360 degrees. So when we go from 0 to 127, that is going to be our first chunk. Then adding another 163. But if we add 127, if you would, they would have put it on here like this, 126.9 plus 169.2. That means that at this point, at the end here, we are at 296.1 degrees, right? From zero, this is zero, all the way to here, adding those two together. Make sense? Okay. And then our last little chunk here is beta 3. And that's the last 63. We had 0.45 degrees. They had 63.7. Okay. And that's to end it. And this would end at 360 degrees. So from 0 to 360 degrees all the way along that length. Okay. The points we need to construct are the curves for beta 1 and beta 2, because then beta 3 is a dwell. Okay, so dwells are always just straight lines at whatever height that you're at. So let's look first at our beta 1. In the problem statement, it said that this was going at a constant velocity. Looking back, remember that was the easiest one, okay? And I kind of wish they wouldn't have picked it, but they did, and that's okay. But remember, we qualified it. So on page 229, this is where it's literally a straight line between the start and the finish. We know that this is going to be hard to accomplish, but we are at a very low speed. We're at, what was it, 14.1 RPMs. That's really slow. Okay, so I guess I would say okay, but it's not the greatest one. But construction wise, super easy. We start at 0, we end at 50, and we break this down into 127 degrees. Now, to get the 127 and how far that would be, if we know that this distance is this distance is 150 millimeters, right? We want to know how many millimeters is 1 degree, right? Does that make sense? So what you're going to do is you're going to take 150 millimeters and you're going to divide it by 300. Oh no, I did that the wrong way. I'm so sorry. Wait. No, millimeters per degree. Yeah, sorry. 150 millimeters divided by 360. Okay. And what number do you get here? Yep. So you're going to get 0.42, and that's going to be, I should have done this a little bit different. Shouldn't have done it here. 0.42 millimeters per degree, right? 0.42 millimeters per degree. Now, if I want to get this distance here, how long is, I'm going to call this D1. If I want to represent 127 degrees along that axis, knowing that it's 0.42 millimeters per degree, how am I going to get D1? Multiply them together, right? Yes. So on our example 9.3, and I know this isn't part of what they're having you do, I'm just going to put scale. Okay. So how do I want to do this? Horizontal axis equals 3 times vertical axis. Okay. So my horizontal is going to be equal to 3 times 50 millimeters, right? So I don't know. I don't have a variable. Horizontal axis is going to be equal to 150 millimeters long, right? Okay. So now beta 1, okay? I'm going to take 150 millimeters divided by 360 degrees, okay? And I'm going to multiply 126.9 degrees. Degrees cancel out, and beta 1 is going to be 150, 360 divide 126.9 times. It's going to be 52.875 millimeters long. Does that make sense? That's how long you would make it. Usually this is the part that people are like, how am I supposed to get the length? So I'm trying to walk you through this so you can know how to construct that. So when I draw it in AutoCAD, this whole length here, all the way to the end to 360, is going to be 150 millimeters long. But this chunk right here where D1 is, that's going to be 52.875 millimeters long. Does that make sense? Okay. Let's do the distance for beta 2. Beta 2 is going to be that same 150 millimeters per 360 degrees. So like our scale factor, if you would. This time we're going to multiply it by 169.2 degrees. That's going to cancel out. So our beta 2 length is going to be 70.5 millimeters long. Okay. So then adding to that, this chunk right here is going to be 70.5 millimeters long. All right. And then beta 3 is going to be that same thing, 150 millimeters divided by 360 degrees times 63.45 degrees. Degrees cancel. And our beta 3 length should be 26.4375 millimeters. I know that's an extreme number of decimals, but that's what it would be. So now if I add these three together, what should be the number that they come to? Should be pretty close to 150, right? Let's add them together. I get 149.8125. So yes, I'm right there at 150. Right. Does that make sense? So the lengths to represent the angles, betas, okay? Any questions on that? Like I said, usually when people are getting started, they're just like, how long do I make that? That's so I wanted to make sure that you knew how to do that. Okay, so those represent the lengths along our axis for beta 1, beta 2, beta 3. So whatever that would be for the problem you're doing, there might be 4, there might be 5, whatever it is. Okay. All right, so once you get those marked off, okay, the very first section here from our 0 up to 50 within beta 1, straight line because it's constant velocity, easy peasy, right? You're not going to have to construct this. I'm just kind of showing you how this is. But the second part of this is cycloidal motion going down. And it's the full 2 inches, but this time we're going over 2 seconds. And as we had just calculated, that distance is going to be 70.5 millimeters. Okay, 70.5 millimeters. So as we look here, this length right here is 70.5 millimeters from where the rise ended to now where the fall is going to end. Okay, and it's cycloidal motion. So we're going to take a line from what would be our 0, okay, for this fall, and we're going to draw a line straight down to the beginning, or what would be the end of the motion. That straight line is going to be then the center of our cycloidal circle, okay? Along that, so you would just construct a construction line going straight through there. That's the line, okay? Now, that's the center, but how big is that diameter? That diameter is going to be 2 times the radius that we see here. So for our example, let's just write out our radius of our cycloidal motion is going to be the height divided by 2 pi. Okay. Now, the height is going to be the distance that we rise or fall. It doesn't matter if it's up or down. And that total distance from that problem was 50 millimeters. We rose 50 millimeters and then it says here we return. So that means we go right back down a total of 50 millimeters. So this H is going to be 50 millimeters. And then we're going to divide by 2 and divide by pi. So our radius should be 7.958 millimeters. You guys get that? That's the radius. So 2 times that would be the diameter. So whether you draw that cycloidal circle with a center radius of 7.96 or whatever it was millimeters, or if you do it as a diameter, just make sure you multiply it by 2. Okay. And its center is going to be, again, along that extended line down. Now, how far do you go? Just out of the way. That's all. Okay. There's no set distance there. Now, once you get that set and you have your 70.5 inches marked off here, you're going to divide this by 6. So you see the dotted lines here? These are 6 even divisions of that 70.5. So the distance between those, if we take 70.5 and we divide by 6, each one of these is 11.75 millimeters between each one here. Okay. So 6 divisions. Then what you're going to do is on that circle, you're going to draw the lines that are here at 60 degrees vertical and horizontal. All right. Then as we number this across, we're going to start with 0 here and we're going to go 1, 2, 3, 4, and 5. Okay. Now, where we start, this is going to be our 0. This is going to be 1. This is going to be 2, 3, 4, 5, and 6. Does that make sense to everybody? So it's in the start of the motion to the end of the motion. If we're down here, 0 would start here and 6 would go to the end in this direction. So you always have 0 at the start of your motion, 6 at the end of the motion. So we're not starting 0 here and going back this way. We're going in this direction. So now when we rotate this in a clockwise direction, we're going to start at 0 here. It's going to be 1, 2, 3, 4, 5, and then I forgot 6 is going to start back up over here. Okay. Now remember, we go from those points and we bring them together in the middle. So 0, 3, and 6 are going to be along this line, which they automatically will be. We had 0, 6, and then 3 is going to be the middle. Okay. 1 and 2 are going to be up here, 1 and 2. All right. 4 and 5 meet in the middle, go parallel to, and that's going to be 4 and 5. Okay. Any questions? Once you get those points marked off, it's going to be a best fit line through those points. Remember, points in AutoCAD are called nodes. So if you want to place the points, you would place a node. All right. Again, if you need help with any of those little things in AutoCAD that we haven't done this term, but you probably did it in previous AutoCAD class, which has been a little while. So if you need a little help, let me know. Okay. And then once we're at the bottom here, we're not quite done with our motion. We have one last dwell. Don't forget that little dwell at the end here, and it's just going to be a straight line till the 360 degree. Okay. And then that completes, and then it would start back over at 0 degrees and then go around again. It would rise 2, fall 2, dwell for a little bit, and come back around. Okay. So as far as what to label on your displacement diagram. Okay. Now I marked up a lot here for construction, but what you see that they have is what you need. So on this example, you need the y-axis labeled with follower displacement and in parentheses, whatever units you're dealing with. Okay. And then you're going to just kind of do a couple and especially the highest point, what that value would be. So in this case, 50 was the high point, right? They put a 25 and then you would start at 0. Okay, you don't have to mark off every one, but just be reasonable with that. Along the x-axis, you just need to mark off, for instance, your betas, because we know that this is 360 degrees in time, right? And so you would do however many motions you have. So in this case, there was 1, 2, 3. So you want to say beta 1 is equal to whatever the angle was that you have for that chunk, okay? And then beta 2 and beta 3. And notice that each one of those are labeled here, okay? And then along this axis, this is just considered time, okay? And then make sure that you have beta 1 is equal to however many degrees it is. Beta 2 is equal to however many degrees and such. Don't mark it off in millimeters along here. This is in, degrees of revolution or degrees, around that circle, okay? And then that would be it. And then just make sure that whatever calculations you do for radiuses or distances along, make sure that you document those for, what's appropriate. Okay. So any questions on example 9.3? So what you need to hand in is don't worry about the illustration. We just talked it through. You were thinking while we were talking, oh, how would I do that in AutoCAD? And you're like, okay, I think I got it, right? You will be creating the diagrams for the 2 assignment problems that you have, okay? But not for the practice problems. But you will be handing in the work that we did together here, for example, 9.3 and 9.2, okay? Hope that wasn't confusing. Does that make sense? Okay.
It's just a lot of stuff.
It's going to be a lot of steps, but it's a matter of just kind of jumping in and doing it. And I have no doubt with your AutoCAD experience and the information that you have in the book and the stuff we went through, you'll probably have a question along the way or 2 or 3, and that's what I'm here for. Okay. But rather than watching me do it in AutoCAD, I think we probably saved about 45 minutes, honestly, in lecture time that I believe you can make that leap. I really do at this point. So, okay, let's take a peek at the homework so that you know what you're going to be doing, okay? The next time we get together, we'll continue on in our PowerPoint. So, practice problems. We did the 3 practice problems here today. Okay, so that would complete the practice problems. We're not done with Module 7, so please don't hand the practice problems in yet, okay? Because there is more that we're going to be doing, but we'll be doing it together the next time that we're together. Then as far as assignment number 7, the first 2 problems you are ready to work on, okay? So let's take a peek at those. That's 9.7 and 9.9. These are found at the end of the chapter. And they're on page 254. 254. So let me go back over here. Okay. So the first problem you're going to do is going to be 9.7. It says we have a cam drive is used for a mechanism that tests the durability of oven doors. The cam follower must rise 2 inches with harmonic motion in 1 second. So that's our first motion scheme. It's going to dwell 4.5 seconds, fall 2 inches with harmonic motion in 1 second, and then dwell for 1 second, and then repeat that sequence. So there are 4 steps here. There's a rise using harmonic motion in 1 second. There's a dwell for a half a second, the fall of 2 inches in 1 second using that same harmonic motion, and then you're going to dwell 1 second at the end. So 4 steps, okay? Determine the required speed, W of the cam, and graphically plot the follower displacement diagram. This is exactly like the example problems that we went over, okay? Exactly like it, but you are now adding the displacement diagram, okay? Let's take a peek at what that displacement diagram is going to look at like and what you're going to reference, okay? So go back underneath here. I'm only going to, in concept, show you the displacement diagram. You're going to figure out all the numbers, okay? So your displacement diagram is going to look something like this, okay? You're going to use harmonic motion. So you're going to go up like this, okay? You're going to dwell and you're going to go down and you're going to dwell. So your 360 ends here and your 0 degrees starts here. You have your first chunk, second chunk, and then third chunk, okay? So this is going to be a beta 1, beta 2, beta 3, and beta 4, okay? This is your rise harmonic motion wise, okay? I know my my scale, if this is 2 inches, remember this has to be 6 inches, 3 times as long. Does that make sense to everybody? Okay. Has to be 6 inches. Now, harmonic motion, we did not do that one. All right. So on the rise here, this is harmonic motion. You're going to make a half circle. The center is going to be here. The radius is going to be 1 inch. The diameter is 2 inches. Okay. You are going to break this into 6 equal segments. Okay. So this is going to be 30, 30, 30, 30, 30. Okay. And this is going to be 1, 2, 3, 4, 5, and 6 at the top. You're going to break this into 6 even segments. 6, not even. But then this is going to be one. I'll do it this way. This is going to be one. Whoopsie. 1, 2, 3, 4, 5, and 6. Okay. This is going to go up here. This is going to be 0.1. This is going to go up here. This is going to be 0.2. This is going to go up here. Gosh, I really made that. This is going to be 0.3 and so on. Does that make sense to everybody? And then through those points is going to be a spline. Okay. Now, the nice thing about this problem is that you can use this same radius on the other side. So this is going to come in this direction. The center is going to be here, but now the motion starts here. So this is 0. And you're going to break into 6 equal segments. So this is going to be 1, 2, 3, 4, 5, and 6. So that means that starting up here, this is 1. Okay? Don't start 1 down here. Does that make sense? Because you're coming back this way. So now this is going to be your 1, 2, 3, 2, 3, 4, 5. So this will be 2, 3, 4, 5, and then 6 is going to be at the bottom here. All right? Now, if I'm looking, let me think. Let me see. Oh man, I was so nice to you guys. It falls and rises in 1 second. This is a mirror. Okay. If this was spread out a different amount of time, it would not be a mirror. You'd have to reconstruct, but you're welcome. It is. All right. So once you construct it on one side, you can do a mirror on the other. All right. And it'll be, in that opposite direction. Now, students will always ask me, do I need to show the construction? The answer is no. But I want to see the points that I see that it was along a spline. Does that make sense? That'll help me. And if I'm leery, I might be like, I need to see the file. Okay. So what I would do if I were you, do the construction on one layer, like on a construction line layer, and hide it. Okay. And then that way, if Kelly says, hey, I'd like to see your construction, all you have to do is pull that up, and then you have to unhide that layer. And then, I can easily see it. But if you say, I deleted the construction, then you're gonna have to reconstruct it. All right. Does that make sense to everybody? If you want to leave it on and you find a way to put this on so it's all nice and readable and you can put your information, fine. But if it's, to me, there's a lot going on here, I would just put your construction on one construction layer and then just hide that layer so that then everything else in your final product can be showing. And then if Kelly says, ooh, I'm thinking I want to see your file, then all you have to do is unhide that layer and I can see your file. Does that make sense? Okay. So that's that. That's your first problem. The second problem that you have is going to be 9, 9. Okay. Now this one is a cam drive packed stuffing into shipping boxes. The cam follower must rise upward 1 inch with cycloidal motion in 1.5 seconds. Okay. Cycloidal we already looked at. You're going to fall 1 inch with cycloidal motion in 1 second. Now this time, notice the times are not the same. This will not be a mirror for you, okay? But the size of the circle is the same, all right? Because it's a 1 inch and a 1 inch rise and fall, okay? And then you're going to dwell for a half inch and then you're going to repeat. Okay. So just 3 steps here in the full cycle, full rotation, but you can't mirror the cycloidal this time. You can use the same circle, but you're going to have a different slope of the line because the time is different. Okay. So, so for this one, determine the required speed of the cam, W. So you have to do the T's and the W's and the betas, no matter what. And then you're going to graphically plot a follower displacement diagram. Again, the construction you can put all on one layer and you can, hide that or leave it. If you feel like it's not really disruptive and it's easy to read all the other labels, then that's fine. But if you find that it's too, cluttered, and there's not much room there, then, do that hiding. And if I say, hey, I want to see it, then you can just unhide it and that's it. Okay. All right. So any questions at all about the first two problems in our assignment at this time? Okay. Like I said, I know I didn't demonstrate the AutoCAD. I fully expect that as you get started, you might have some questions. All right. And that's fine. All right. That's why I'm here. So I encourage you to work on getting started on this assignment. And then that way, if anything does arise, you can get those answered while I'm here. All right. Otherwise, the rest of the time is yours. And let me know if you need any help on anything. I'll stop the recording.